Thanks for the invitation. I will talk about reproducible workflow and some software tools that me and Dr. Niamh Cahill from Maynooth University, we are using now to develop our project. I'll just talk about very briefly about some data science workflows, and specifically talking about data science for obviously data analysis. So we know that this is something that data analysis is not something that is linear. Actually, we always have one step after the other, and this is a very iterative process, and we learn from each step. So each step that we are going through, we are able to refine what we are doing, and also we are able to find out how to proceed to the next step. So there are 5 core activities in data analysis, and I'll just tell you from where I borrowed this. So the first thing is stating and refining the question. The second thing is exploring the data and then building formal statistical models, and then interpreting the results and communicating the results. So this is called the epicycle workflow, which was defined by Peng and Matsui in 2018. And for each of these 5 core activities, there are also these 3 steps, which are set expectations, collect data and compare with your expectations, and revise expectations or fix the data. So this 3-step process, then it's called the epicycle of data analysis, and we can use this for all of those five steps I told earlier. And actually, you see that I'm focusing here on the aspects of data, which is the tools that we are using now. We are using to deal with a big set of data, and we are trying to make this somewhere more reproducible. So the elements of reproducibility, first of all, well, actually we have always these 4 elements to make something a research reproducible: the data, obviously, the code, the documentation, and how will you distribute all of these things. So the data, usually you have to provide in the exact same way you made the analysis. The code, so this is something important, that it must be, for example, executable at once. It is much better if you can use something like dynamic documents to make this even more reproducible. And the problem is that we always have files, auxiliary files or data files that we have to share with this data. So this is something that we can deal with too. And the documentation, so always try to describe to humans what you are doing or what your code is doing. And the distribution, that's probably one of the hardest things, how to distribute your code and your data, especially if you are using a big set of data. So this is what we will talk about. So the key for these tools, we have to always keep in mind that all of these steps must be reproducible by anyone. And the first thing is always make it reproducible for yourself, and then reproducible for our team, and then to anyone else. So there is this quote from Justin Kitts from a book from Reproducible Research, in which he says that a scientific project is computationally reproducible with another research, including the future you. And this is, I think it's very important, because sometimes even some things that we did in the past, we are not able to reproduce. So you have to think about the future self at first. So if another researcher is able to recreate all of the results, given only a set of files and the instructions to run it. So we are talking about reproducibility because we know that replicability is hard and sometimes even impossible. So we have two options, or do nothing, or at least try to reproduce the study. And so the general idea, according to Roger Peng in Science magazine, the published article of him, the general idea is to create a minimum standard for judging scientific claims. So, for example, if you have a publication, it's not reproducible. If you have a publication plus the code or plus code and data and linked in executable code and data. So this is going into the gold standard, which we are searching. Actually, the gold standard would be the full replication, which we know that's not always possible. So about the tools for this collaborative workflow, I just borrowed some ideas from this paper published in Nature in 2018. So, for example, some aspects is use code and go open source, which I really find something very important. Tracker versions, as you know, use GitHub, GitLab, or any other tools like that. Document your analysis, possibly using dynamic documents like iMarkdown or Quarto and these kind of tools. Automate everything, so you can automate how these files will be running or how this will run, for example, in a GitHub repository using GitHub Actions, for example. And I will now just focus here on these two aspects, on replicate your environment and archive your data. Because for this specific project we are using, this is now the what we are trying to do. So the first thing is to replicate our environment. It means that you have to make your project self-contained, or at least almost self-contained, in terms of packages and softwares that you use for that specific analysis. So virtual environments are one type of replication of environments, and container virtualization is another one. So when we talk about virtual environments, we are saying that we are just recording all the packages we are using. And so I'm really an R user, so always that when we are using R, we always use several packages, different packages, and this is not really straightforward for anyone who will use your project afterwards to have all these packages on the same versions and to assure that they will work in the same way. So these virtual environments is something that for the R community is not so not started so long time ago. It started with a package called PackRat, and then it evolved to this package now called renv. In Python, people who use Python already know this from several years, because there is the venv aspect in which you can save specific versions of Python and packages. But it's the same, almost the same concept, but in R we use the renv. And about container virtualization, it's the virtualization of the operating system level, and we call these containers, and probably most of you already heard about Docker, which is the main tools for this. So in the reproducibility spectrum, we have the script, then script plus data, then renv, Docker, and you can actually use renv and Docker at the same time. So to replicate our environment, what renv does is that the problem is that you always have in your machine or in a server, you have your library with many packages, and all of your projects will try to find those packages in that library. So the solution was that renv made a global package cache, and you have, for different projects, you have different libraries. And these libraries go search for these packages in this global cache. So this solves a lot of problems, and it records all the packages you are using in a specific project with that specific versions. About containers, we have the two types of virtual machines. We have the virtual machines by itself, which you can have you have your infrastructure, but you have to have a guest OS, and this sometimes is not really straightforward. And with Docker and the structure of containers, we use most of shared uh, operating system files to build these containers, so it's a little bit more straightforward and easy to follow. And another aspect is then to archive your data. So you obviously can use data repositories like Figshare and Nodo and other repositories. But other thing is that you can make your data usable and accessible specifically with universal formats. So for example, you can distribute your data in text format, as you know, but it's not always very possible or feasible, as I will show you. And there are also the universal formats like SQL and its variations. And now we have Arrow and Parquet, which I will talk about now. So our project is dealing here in Maynooth University with extreme sea levels. We'll try to estimate extreme sea levels for Ireland. So we are using this the GESLA dataset, which GESLA is Global Extreme Sea Level Analysis, which is a project that which is led by these authors, Woodworth and Haig, and they compiled and gathered data from all over the world, as you can see in this map, from tiny gauges all over the world, specifically from 36 data providers. And the current version of this database contains more than 90,000 years of sea level measurements from more than 5,000 records. So it's a real big data set. So this data set is distributed now as a single zip file of more than 5 gigabytes in size. But when you extract this file, there are these more than 5,000 CSV files. And even though they are text files, as you know, the total size is almost 40 gigabytes of data. So they made available a MATLAB and a Python script to deal with these files. So you are able, using these scripts, you are able to read a single file or a list of them and make them available in memory. However, this is really not a good thing because this data set is so huge that, for example, in R or Python, if you load this data set in memory, you can actually, it can actually probably not load at all, or even if they load, you will not be able to make any operations with this huge data, which will occupy probably most of your REM memory. So our goal now, the first step of our project is to standardize the distribution of this data set. So to make easier for anyone to fetch the data from whatever part of the world they need without actually downloading everything. And to achieve that, we are converting the CSV files to a lighter and more universal format. We are also creating a web interface with Shiny to filter the data. And we are also creating a companion R package to fetch this data and possibly using an API. So just to talk about what is this Parquet format, it's from the Apache project. So it's a fairly new format for big data. It's important that it's an open source format. It's column oriented and it's designed for efficiency and thinking about data storage and retrieval. So it's a format that can be read by many languages. So there are packages and connections with R, Python, MATLAB, C++, and many other languages. So with this type of formats, the Parquet format, we can use another software called the Apache Arrow, which is actually a language also from the same project, to use in-memory analytics. So in-memory analytics means that you will not compute actually everything directly in your CPU. It will compute internally in this spatio-temporal language, and then only after it is computed you can just retrieve the results. So this has many advantages because you don't need that. You don't actually need to load all the big data in your memory, and you and the operations that you make with these big data, they will not actually they run pretty fast because it runs in this type of in-memory analytics. So after we converted all those CSV files to the Parquet format, we jumped from 40 gigabytes to 7 gigabytes in size with the same files. We were able to store these files in a AWS bucket and Amazon, and now we can just connect. I'm talking specifically about R, but you can do this with Python or any other language. So we have the Arrow R package to connect with this bucket from Amazon, as you can see in the code. I just connect from the using the function S3 bucket to this data set, which is stored in AWS. And you can see that after I load, it's instantly loaded. And the object that contains all of those data sets, you can see by the number of rows is 1.17 billions of rows. And the object size is just 500 bytes. So it's really small size for such a huge data set. And you can make any operations you want using the dplyr verbs in R to operate in this data set. And using this concept, we developed this interface, which will be made available soon. So this web interface, using all these concepts, we created this web interface in which this interface is already connected to the S3 bucket with the whole data set, but anyone will be able to filter the data set and take a look at some plots and maps and download only the filtered data in CSV format or the Parquet format. And the other thing is what we are finishing now. Obviously, we are using I told about RNF because we are using RNF in this project, and we will develop an API interface with our package Pumbler. So instead of using, you will always be able to use this interface to filter data, but with the IPA, our idea is that you can just use code, so you can make programmatically filter data from your code, which will link to the AWS bucket, and then you have all the data and all the process in your script. So you will not even need to download the data to make a reproducible code with all this data set. And possibly also we will develop a Docker image with all of this code and data as well. So this is it. I would just like to thank the Geological Survey of Ireland, the Science Foundation of Ireland, and Maynooth University. And thank you very much for your time, and I'm available if you have any questions.
Thank you, Fernando, for that talk. Does anyone have any questions from in the room? Oh, sorry, I'm going to stop the recording first.